In this video, we're going to have a look at a general method for computing the derivatives of all inverse functions. You may wonder why we want to do that, since inverse functions are functions themselves, so why can't we simply use the definition? It turns out that the method I'm going to show you allows us to compute derivatives of inverse functions in a much easier way than by using the original definition of derivative. But I want to give you a little bit of a motivational example. Now, remember the power rule? Well, we know what it looks like, and in fact, we have been able to prove it in some cases. For instance, if we look at a natural number, which means 1, 2, 3, 4, 5, etc., positive integer numbers, then we can prove that the power rule works by simply direct check, which means use the definition of derivative. Well, with low powers, all we need to do is use the definition of derivative, expand the power, do the appropriate simplifications, and get to the answer. With higher power, we may need to use something called the binomial theorem, but again, it's not very difficult to do it. We can also prove that the derivative of x to the minus n follows the power rule, so it ends up being the original exponent times x to the original exponent minus 1. And the way we have done this is by using the quotient rule. You may not remember how we did that. Well, you may want to review that particular video. But how do we know that the power rule works with fractional exponents? Okay, so how do we know that the derivative of x to the power 1 over n follows the same rule? We haven't proved anything to that effect. The technique I'm going to show you now will allow us to get a very simple proof of this fact, which does not rely at all on complicating algebra. Now, the trick is to realize that our function comes from the regular power x to the power n as its inverse, right? Taking the nth power and taking the nth root, which is the power of 1 over n, are inverse functions of each other. And we know how to compute the derivative of x to the power n. So, more generally, we're going to ask, if we know the derivative of some function, can we in fact compute the derivative of its inverse function? Because if we can, now that we know what the derivative of x to the n is, we can get a proof for what the derivative of x to 1 over n is and confirm that it also follows the power rule. Well, fortunately, and as you can imagine, the answer to this question is yes, and here is how it works. Well, the theoretical thinking goes as follows, and pay attention to what I'm about to say because of something I'm going to say at the end of this explanation. We're going to use implicit differentiation. So we're starting from a function, and we know that this function is the inverse of some other function whose derivative we know. So what we're going to do is we're going to apply that original function on both sides. So on the left-hand side, we end up with f of y, and on the right-hand side, we end up with f of f inverse of x, which is just x. Now we're going to compute derivatives on both sides, and that's the heart of implicit differentiation, right? So computing the derivative on the left-hand side means applying the chain rule. So we're going to have to compute f prime at y and then multiply that by y prime, which is what we're looking for, remember? And of course on the right-hand side the thing is easy because the derivative of x is just 1. Okay, so y prime is what we're looking for, and it's there all by itself, so we can isolate it. Well, we're almost there already. Notice that we already have an answer for what y prime is. The only problem is that this answer is in terms of y. But we know what y is, right? Y is, to begin with, our f inverse of x. And therefore, all I need to do is put f inverse of x in place of y in my formula. And I can see some of you just dropping your jaws and say, what? That formula looks very complicated and confusing. And I would agree with you. It's actually not that bad once you become familiar with it, but it is a formula where you have to compute the derivative of f and then evaluate the derivative of f at the inverse of f itself. That can be a bit confusing and messy, but it turns out that if we actually follow this same method, we end up with some very simple proofs of derivatives of inverse functions without really having to worry too much about the complication or the confusing aura that surrounds this particular formula. Let me show you what I mean. Back to our root function, remember we're trying to check that in fact the power rule applies to a function of the form x to the power 1 over n, knowing that it does apply to a function of the form x to the power n when n is a natural number, so a positive integer. Okay, so what we're going to do is we're going to follow the method, which is what? Well, first of all, apply the original function on both sides. In this case, that means applying the nth power on both sides. So we end up with y y to the n is equal to x. Then we're going to take the derivative on both sides implicitly, which means using the chain rule. So on the left hand side we end up with the derivative of y to the n. On the right hand side we end up with 1. And again, developing the derivative on the left hand side gives us the derivative of the outside portion, the nth power, and that is what we already know. We know that that's equal to n times y to the n minus 1, but we have to multiply by the derivative of the inside, which in this case is just y, so we end up with times y prime equal 1. And remember, as I showed you in the general thinking that we used for this technique, now we have y prime all by itself. So we're going to isolate it. So y prime is going to be equal to 1 over n times y to the n minus 1. Remember, the trick now is the fact that we know what y is. Y is x to the power 1 over n. So all we have to do is substitute it in. And now from here on we're done. It's just a matter of a bit of a basic algebra with exponents. So a power of a power is obtained by multiplying the two exponents. That gives us 1 over n over times n, which is just 1, minus 1 over n times 1, which is 1 over n. Okay, so all we have to do is now take that x and move it up to the numerator by taking the negative of the exponent. And that gives us, surprise, surprise, 1 over n times x to the power 1 over n minus 1, which is exactly what the power rule was telling us. Okay? So notice again, this technique is fairly simple. So what you do is you apply the original function, take the derivative implicitly. So for y prime, substitute back the original value of y. And it allows us now to confirm that in fact the power rule does apply to fractional powers. I'll leave it to you as an exercise to combine maybe this with some other rules that you already know, maybe some chain rule or something like that, to find out that the power rule actually works for any fractional power, even the ones that don't have just a 1 in the numerator, but any fraction of the form m over n, say. Well, what else is this good for? Not only to figure out the derivative of a fractional power, but also to get the derivatives of a whole bunch of other useful functions. For instance, we can compute with this method the derivative of ln x. Why? Well, because ln x is the inverse of the exponential, and we know by now how to compute the derivative of the exponential. We can also figure out what is the derivative of arc sine x, because of course that's the inverse of the derivative of sine y. Or of sine x, sorry. So it's equivalent to sine y equals x. And therefore, we can use whatever we know about the derivative of the sine function to figure out what the derivative of the arc sine is. Now, if you have not seen what the derivative of sine function is yet, well, just hold on to your hat. We'll get there soon. And in the same way, for hyperbolic functions, we can compute the derivative of the inverse cosh or inverse sinh or inverse anything else, because of course they are inverses of direct functions whose derivative we can compute. And there are many more examples that we can look at, but we'll look at them as we encounter these ones. Just remember, what is not going to change is the technique. And once again, remember, the technique is start from your inverse function, apply the original function on both sides, differentiate implicitly, and then solve for y prime and substitute back in terms of x. And that's all.